All right, great, thank you. So as An has introduced, I lead the Materials Virtual Lab. So we are a group of material scientists who focus on the application of materials informatics, which is the combination of computational material science with data science to accelerate materials innovation. So because there are so many talks over the course of the summer, so I have decided that I will actually make my talk very, very focused rather than giving you just a very big picture machine learning talk or for machine learning for materials talks, right? So today, what I'm going to talk about is one specific kind of machine learning, which is called graph deep learning, and how it actually applies to material science. Okay. So I'm sure over the course of the summer you have seen so many seminars. You know that machines actually have been used in material science for a very long time. All right. So by now, the application of using computers to actually design materials has been done for at least say 2 or 3 decades, ever since the computer was first invented, right? So a lot of the computational material science that you see today are what is called first principles computational material science. And this is really based on quantum mechanics, right? So there's this very famous quote from Paul Dirac, which says that the underlying physical laws necessary for the mathematical theory for a large part of physics and the whole of chemistry are thus completely known, and the only difficulty is the exact applications of these laws leads to equations that are much too complicated to be soluble, right? And nevertheless, if we actually do some approximation, so we take our Schrödinger equation, we make some approximations such as density functional theory, we can still solve this equation for reasonably complex systems, right? So by plugging this into a computer, we can and applying them together with some phenomenological laws like the laws of thermodynamics, kinetics, mechanics, and so on and so forth, we can now today actually predict a lot of the properties that we want for designing materials. Okay, so things like the energies, the forces, the electronic structure, the mechanical properties, and so on and so forth, right? And in fact, today, computers have become so powerful that we can actually do automation of such calculations such that we can generate very, very large quantities of data, right? So as the host has just presented, I'm actually part of the materials project, and this is a big project where we took all the known crystals in the inorganic crystal structure database, and we automate density functional theory calculations across the entire set of known and as well as some hypothetical compounds to basically calculate all their properties such as the energies, the band structures, as well as things like the elastic tensors. Okay, so today you can actually click on the materials project and you can go look up any property that you wish for any of these about 140,000 materials at this current time. Okay, so given this, a natural question that most people have is, well, since we can already compute properties using things like density functional theory, why do we actually need machine learning, right? So I want to show you why it is that just simply doing first principle computations is not enough, right? So this is a data history of the materials project. So the materials project started in about 2012. Today is about 2022, so this chart is about 2-3 years late, 2-3 years out of date, but by and large the numbers haven't changed all that much since 2019, right? So what you will notice is that in the early days of the materials project, we have a very, very healthy growth in the number of material properties that we have. So we started with about 1,000 structures and energies, and by 2019 we have about 140,000 materials and energies, right? What you will also notice is that there are some properties for which we have much less data, right? So for example, the elastic tensors, we actually only have about 14,000 of them, so 1/10 of the number of structures we have in the materials project. We have the elastic tensors as well. And this is really because there are just certain properties that are just much more expensive to calculate compared to just relaxing the structure and getting the energies, right? So, but even things like for the energies, we don't actually have the ability to compute everything, right? So I like to give this example. Let's say you just take a very, very simple perovskite unit cell and you create a 2x2x2 supercell, and you assume that you can have 10 different candidates for your A site and 10 different candidates for your B site. So this is just a very, very small cell, right? And just by making a very naive estimate, we can see that you have on the order of about 10 to the power 7 crystal structures, right? So in essence, what I'm trying to say is that materials design in its very nature is combinatorial, right? So when you try to swap different elements and try to think about what new materials can potentially be out there, you actually have a very large universe of materials, right? And this universe of materials is much larger than whatever materials that has already been computed or discovered, and we just cannot simply use first principle calculations to compute all our way to 10 to the power 7 materials today, right? So the good news though is that because we have set up databases like the materials project, we now actually have enough data to try to build machine learning models that can learn from the existing data that is already computed, and we then try to use those models to predict properties of materials we have not yet discovered, right? So in essence, what we are trying to do is to use machine learning as an accelerator to predict material properties. So this is the outline of my seminar today. So I'm going to start by giving you a very quick introduction to machine learning for material science. Not too much detail, it's really more the broad concepts such that you understand what I'm going to talk about. I'm going to then go into a very specific kind of machine learning model, which is based on graph neural networks, okay? So this machine learning model is what we call the materials graph network, which we call MEGNet for short. These are essentially mathematical graphs with message passing, and I'm going to go into the architecture and how you actually train machine learning models for them. At the end of this MEGNet section, I'm going to start giving a hands-on tutorial of how you will go about using existing pre-trained models, pre-trained MEGNet models to predict material properties, okay? And I have done this in a way in which you can actually follow along the hands-on using Google Colab by yourself. So feel free to start your browser and go to Google Colab and follow along when I start this section, okay? Now for the second half of my talk, I'm going to talk about how we can actually overcome certain issues with materials data, such as the scarcity issue and the quality issues by adapting graph neural networks. And finally, I'm going to talk about a very exciting development that came out of our group in the past few months, which is what we call the M3GNet, which is the materials graph network with 3-body interactions. And here we are, after this, I'm going to end off with a second hands-on tutorial where I will talk about how you can use M3GNet to do structural relaxations, okay? All right. So let me start with the first section. So I think maybe you have already heard of machine learning from some of the other speakers in the summer session, but I'm going to just reintroduce it. So machine learning basically is the scientific study of algorithms and statistical models that allow computers to basically perform a task without explicit instructions, right? And what you rely instead on is basically patterns and inference. In other words, once you actually have the algorithm, you then give the machine, the algorithm enough data and input and output data, and what the model will do is that it will automatically learn the relationship between the input and output, right? Now, as many of you may well know, machine learning has a big impact on our world today. So There's a lot of hype around it. Every time you hear about self-driving cars, that's actually one of the key things that needs to be developed is a machine learning model that can detect things like obstacles or keep your car in the lane. But even less sexy things like weather forecasting, this is again based on machine learning models and has been for a long time. When you go to your Netflix viewing recommendations, those are again based on some machine learning model that learns what you actually like to watch. And of course, you have all heard about how today machines can actually defeat even the world best player in Go and chess in those games. And again, what's powering that is basically a machine learning model, right? Now, when we talk about machine learning, there are many different kinds of machine learning algorithms. There's what is called unsupervised learning. There's something called supervised learning where you actually give the machine learning model an input and output to learn. And finally, there's something called reinforcement learning where you learn from real-time data, right? So by and large, for most of the machine learning that you see for materials out there, it is based on supervised learning where you actually have a data set that you actually start to learn from, okay? Now, where is machine learning useful in material science, right? So I already talked about one set of problems, which is you essentially when you are trying to do materials design and you're trying to explore a very large space of materials, that's one area where machine learning is extremely useful, right? So in other words, you have too many things that you can potentially compute using your standard DFT calculations, and you essentially want to use machine learning models to scale with respect to structural and compositional diversity. Now, there's also a second set of problems where I'm going to talk just a little bit about today, which is problems which are too large to compute, right? So most of the DFT calculations that you see performed today are for system sizes that are just maybe up to a few hundred atoms big. And you really cannot go beyond that easily, right? Because DFT scales with respect to n to the power of 3, where n is the number of electrons, right? So if you really want to simulate something that is closer to real world materials, so something like this, where you have grain boundaries and multiple different species in your system, this is something that you cannot easily do using just DFT alone, right? So for example, this model size that I show here is about 1 million atoms, right? So to simulate 1 million atoms, you can't actually do DFT calculations. And here really you can also use machine learning to build potential models that allow you to scale with respect to system size, right? And finally, there's one third set of problem that machine learning is being used in material science is basically for problems that are beyond our understanding, right? Or rather to extrapolate. So for example, if you work in spectroscopy, one of the things that you're interested in is after you measure a spectrum, you may want to derive certain materials insights, like for example, what is the local environment around an atom from the Zein spectra. And this is something typically that is done by humans, right? They basically compare that spectra with some reference spectra, and you try to say, well, this looks a lot like this material, so the local environment is the same. Now, that is a very slow process, and of course, we can automate that using machine learning models. So when we talk about machine learning in material science, you typically follow a five-step process. Okay, so typically you start by identifying the target and problem. So whether this is where your domain knowledge as a material scientist comes in. Whether the problem is worth solving, can you actually solve it using simpler means? So for example, if you are interested only in system sizes of 10 atoms and you are also just working with say a few thousand possibilities, there's really no good reason to use machine learning here, right? But finally, whether the target in fact can be learned, right? Do you actually understand enough about the target such that you know what sort of inputs would likely correlate with the output, right? So that is actually a very important thing that a lot of people don't think about when they do machine learning in material science. They simply just throw different features at a problem and hope that one of them sticks. But that is actually seldom the case, right? The second step in the machine learning workflow is that you actually need to collect data. The good news is that there's a lot of existing data sources that today. So for example, I work on the materials project and I exclusively use the materials project, but there are other big databases of material properties out there like OQMD and AFlow and Nomad that you can use. There's also the experimental databases like the ICSD as well as other sources. Now, if in a lot of cases you actually will have to generate your own data, and again, here is where a lot of the open source material software such as PyMatGen and Fireworks and AIDA actually comes in. They help you automate your calculations to generate a large quantity of materials data from which you can then use to build machine learning models. Now, the third step is really deciding what sort of model that you want to use and what sort of featureization you want to use, right? And this is actually the primary topic of my talk, right? So there are two big types of features that are used today. One are called elemental features, in which you just derive the features from the elements, the properties of the composition of the elements itself. So things like, well, iron has a certain electronegativity, oxygen has a certain electronegativity, and you then use those as features in your machine learning model. There's also features that have the structure of the material incorporated in them. So things like what are the coordinates of the atoms or what are the neighbor distances in the atoms, right? And unless you actually incorporate structural features in your model, you will not be able to do material science across the entire diversity of structures that are out there, right? So my group, we seldom work on elemental features alone. In fact, we almost exclusively focus on machine learning models that actually incorporates both composition and structure. Okay. There's also the training the machine learning models. Again, here you have plenty of open source software out there, things like scikit-learn and TensorFlow. I'm not going to go into them. But I just want to highlight that you actually also have material science specific machine learning models that have been developed over the past few years that are very, very useful and exciting if you are just starting out in machine learning for material science. And finally, you then apply your machine learning model to whatever problem you're interested in. And today I'm going to give you a few examples of how we have applied machine learning models. Okay, so so I'm going to move on. So the next section of my talk is going to be introducing to you one way of describing materials for machine learning, and that's called using mathematical graphs with message passing. Okay, so graphs are actually a natural representation for molecules and crystals. Okay, so if you think about your atoms and bonds in a material, you can represent them using a graph where essentially your atoms are the nodes in the graph and your bonds are the edges in the graph, right? And in graph deep learning models, basically what you have is that each of these nodes and edges are represented as a vector of numbers, right? So in what we call the materials graph network or MEGNet, this is basically the graphical mathematical graph representation for a material. You have your atoms, each of them has a vector. You have your edges, each of them has a vector. And we also have this global state variable, which is also a vector. This essentially is used to represent overall properties of the entire material as a whole, right? Now, when we start with building the materials graph network, we usually initialize the materials graph network by using some information about the atoms. So for example, the atomic number is a potential input that can be embedded into this vector. And for the bonds, we usually embed something relating to the distances that are between the atoms. Okay, so this is, for example, in the materials graph network architecture, we use what is called a Gaussian expanded distance, which is this expression over here, e to the power of negative r minus r naught, which where r naught is the equilibrium bond distance between these two atoms. Okay. Now, a graph convolution neural network basically works in this way. What you do is that you first apply a series of updates, right? So for example, let's say you first start with a bond update. You basically, for example, for this bond, you take information from the atoms that are connected to this bond, and you basically pass that information together with information from the global state, and you update the bond vector using some bond update function, right? And using the information that you have from all these vectors. Now, you can follow that with an atom update, where you basically update each atom with information from the bonds that are connected to it, and as well as the global state. And then you follow, finally, you have a state update where you update the global state with all the information from all the atoms and bonds. Okay. Now, so the key thing here is really what are these update functions, phi e, phi v, and phi u. And in all case, in graph deep learning, basically what we do is that we approximate all these update functions using feed-forward neural networks. Okay, so the reason why we use the feed-forward neural network is because of something called the universal approximation theorem, which means that any sufficiently deep neural network can actually approximate any function. Okay, and the reason why we use something like this is really because of our own we really do not know what this update function should look like physically. So we are using feed-forward neural networks to basically learn what's the functional mapping for these update functions. Okay. All right. So each of the whenever you have a set of all those three updates, you have what we call a magnet block, right? So you have all these three updates. This forms one single magnet block, and you can actually stack multiple magnet blocks to basically form models of arbitrary complexity and locality of interactions, right? So if you actually have multiple magnet blocks, for example, your information can flow from one atom to the next atom to the next atom after that. So then your locality, your interactions that you can see are much further away, right? Now, the other thing that we did was basically, instead of just using the atomic number as the input for our atoms, we actually map it to a embedding vector. This is a length 16 embedding vector for our atoms, and we use that as the starting point for our magnet model, right? And after that, you basically have some concatenation and followed by some deep neural networks, and basically what you have out there is an output layer that gives you your prediction, right? Now, one of the key things about my group is that we firmly believe in open sourcing all our software frameworks. So the magnet model is actually open source at GitHub, and today we in fact are going to use this GitHub repository to basically run our example notebooks, right? And if you are interested in looking at how the architecture is implemented and also making your own changes to the architecture, you are welcome to clone this GitHub repo and use it in your own work. Okay. So in the next few slides, I'm going to show you some information on the performance of the magnet models. So the primary topic of my talk today will be on crystals, but magnet is of course not restricted to crystals only. So there are some of you who work on molecules. So this is actually the performance of magnet on, we actually benchmark the performance of magnet on a set of 13 different properties of the QM9 molecular set. And this is just a quick summary of some of the results. At a point in time where we actually develop magnet, it actually has state-of-the-art performance that for in at least 11 out of 13 of those properties. There have been actually models that have further improved upon this performance and today, but by and large, this performance is already extremely good, and it is well within what chemists generally consider as chemical accuracy. Okay, so for example, things like the internal energy, the Gibbs free energy, the HOMO and LUMO levels, and the heat capacity, you can actually predict the properties of all these molecules to a very high degree of accuracy, right? Now, you will notice that, for example, there is one which is called MEGNet and the other one is called MEGNet Simple. The difference between the two is just in this particular model, we actually use a very complicated set of input features based on things like the aromaticity of the bonds as well as the electronegativity of the atoms and so on and so forth that were used in this ShueNet model. We actually found that was completely unnecessary. So even if we use a simple model where we just use the atomic number as the atomic feature, we can actually get a model that has very comparable performance to the full MEGNet model, right? And the reason is because the graph neural network actually is able to learn the mapping from, say, the atomic number to something like the chemical nature of that atom. All right. Now, we also trained a MEGNet model on several MEGNet models on the properties of crystals from the materials project. So here you will see that, for example, we can predict the formation energy of any crystal to within about 28 MeV per atom. This is basically good enough for you to make a lot of decisions about whether something is likely to be stable or not. We can predict the band gap to about 0.33 eV. We can also predict things like the Bow and Shyue modulus as well, right? Now, very frequently, one of the main questions that people ask is, well, is this 28 MeV per atom good enough, right? And so this is actually work that was done some time ago by Wenhao Sun, who is now a professor at University of Michigan. He basically looked at the E above Hao for all the crystals in the ICSD. And what this work found was that basically about 80% of the materials in the ICSD fall within about a range of 70 to 100 MeV from the convex hull of the 70 to 100 MeV from the convex hull, right? And this accuracy of 28 MeV per atom is well within that 70 to 100 MeV per atom. And so it is good enough for you to make determinations of the stability, right? Now, you also notice these numbers in brackets. These are basically the number of crystals that was in the data set at the point in time where we actually trained this MEGNet model. So there were about 60,000 crystals in the materials project at the time. But what you'll notice again is that the data set for things like, for example, the accurate band gaps, which is much less, almost about half the data set of the formation energies, and the data set on the Bow and Shyue modulus is even smaller. So when you have much smaller data sets, you actually have accuracies that are a bit more suspect, and this is where we actually did a lot of work trying to address this data scarcity issue, and this is something that we will go into in the third section of my seminar. Okay, so one way you can address this problem is actually using what is called transfer learning. So what we found was that if you actually just take the embedding vectors from our formation energy model, which has the most data points, and we just reuse those embedding vectors, we don't actually retrain them, and we just build a new MEGNet model using the same embedded vectors for the band gaps, we can actually decrease the mean absolute error of our band gap from 0.38 eV to about 0.32 EV, and it also converges a lot faster. In other words, just by doing this kind of transfer learning, we can actually, using models that have already been built on a very large data set, we can actually significantly improve the model performance on a smaller data set. Okay. Now, one of the most exciting thing about graph-based deep learning is that because it's such a natural representation for materials, we found that when you actually train your MEGNet models on things like the formation energies, the model itself actually learns chemistry from the data, right? So here what we did was that we took the 16 length 16 embedding vector for each of the elements, and we basically plot the Pearson correlation coefficient for between pairs of different elements, right? So this plot basically shows you the pair correlation function between the embedding vectors for each of the different elements with every other element, and we actually sorted the elements by Mendeleev number. Now, what you will notice is that there is definitely a trend, right? So for example, you see here you have all the alkaline metals, and all the alkaline metals have very strong Pearson correlation with one another, right? And similarly, you will see the same trend for things like the rare earths. You'll see the same trends for things like the alkaline earth metals, and so on and so forth. So in other words, what we see from this plot is that the MEGNet model has actually learned the periodic table of the elements, right? So the periodic trends in the periodic table. So we know, for example, that lithium and sodium has very similar chemical properties. And here, the embedding vector has a very high correlation with one another, even though we didn't start off using a very highly correlated embedding vector, right? So the machine learning model has naturally learned a chemistry trend. We can also do what is called TSNE plot, and again, what you notice is that here all your elements that are very similar chemically actually are clustered together in this TSNE plot, right? For example, all your alkaline metals are all over here, your alkaline earths are a bit more spread out, but all your rare earths are all over here, and you notice that these are all things that you would expect in terms of the chemistry similarity of all these elements, okay? All right, so we have now come to the first hands-on session, okay? So very exciting. So I'm going to stop share. Before we go on, so one of the things that you will need to do to follow with the hands-on session is to get what is called a Materials Project API key, okay? So the way that you will do this is that you go to www.materialsproject.org. If you do not already have an account with the Materials Project, you need to sign up for an account. You can do that using your Google account. That will be by far the easiest, or you can use one of the many different ways in which you can sign up for an account. But the key thing that you need to do is that you need to click on this user icon over here. You go to your dashboard in the Materials Project, and what you see in the dashboard is this thing which says the API key. So I have blanked this out for mine, but basically you will see a string of alphabets and letters over here. That is what is called your Materials Project API key. And what this API key allows you to do is to download large quantities of data from the Materials Project in a programmatic manner, right? So instead of clicking on every single material and just looking up the properties one by one, you can, for example, say download all the elastic constants that we have in the Materials Project for every single crystal, right? So that is basically the use of the API key. So you will need this API key to do your to run the example notebooks. Okay. Now, the other thing that you need to do is you can go to after you have obtained your Materials Project API key. What you will do is that you go to colab.research.google.com, and you will be introduced with this pop-up which asks you to basically set up your to open a notebook, right? You can either create a new notebook, but here what we are going to do is that we are going to use the notebooks that I have already written for this particular seminar. And what you need to do is that you click on the GitHub tab, you search for the Materials Virtual Lab, you click the search button, and what you will get is a drop-down list of repositories that you can that are developed by my group. You click on this and you will be able to see and search for MEGNet and select MEGNet, and you will actually see a list of Jupyter notebooks that we have developed, and the notebook that you should be looking for is this thing which says property prediction with pre-built MAGNet models. And once you click on that, you will actually open up the GitHub the notebook in Google Colab. Okay. Now, I do need to caution something. So Google Colab, for some reason, it is very outdated. It actually uses Python 3.7, even though the rest of the world, people like NumPy and SciPy has moved on to Python 3.8 and above. So until it is upgraded, the steps that I'm going to show you, they will install an older version of PyMatGen that has there's an old MP raster that only supports the legacy API key. So the API key that you actually get from the front page today, you won't be able to use it in your Google Colab notebook because the Google Colab notebook is running on the legacy API key. I'm going to provide you with an API key that you can use. But if you run the notebook actually from your local computer and use your own API key that you get, you should be able to do that if you install all the latest versions of the dependencies. Okay. All right. So let me stop my share and we will. I'm going to share my next set of my browser. Okay. All right, so this is the Google Colab page. Okay, so if you click on Open Notebook, as I mentioned, you go to GitHub, you type Materials Virtual Lab. There are a lot of repos. As I mentioned, we are firm believers of open sourcing all the software that we write. So you go to MEGNet. There are a number of plots, but what you need to look for after you keep scrolling down is this thing called property prediction with pre-built MAGNet models, right? So you click on that, and what you see is this notebook over here, okay? And so I have taken the opportunity to basically write a very detailed notebook about how you actually go about using MEGNet, right? So here, if you are running from Google Colab, one of the first things you need to do is to install PyMatGen and MEGNet because those don't come as default on the system. So you will see this thing which says that the notebook is not authored by Google. You just say run anyway. Don't worry, the notebook is safe, okay? And you have to wait for a bit of time for the notebook to finish running. Okay. Now, while the installation is running, this will finish not in a few minutes. Basically, first of all, what you will do here is that you will actually import several things. Okay, so from the MEGNet, you will import something called load model as well as import the available models. So what we have and from PyMatGen, you will import things like the structure and lattice as well as this MP raster, which is basically the high-level interface to the Materials Project API that we have developed in PyMatGen. Okay, so by default, MEGNet already comes with some ready-to-use models. So the models that I showed you previously, all the results, we have actually made those available within the MEGNet code itself. So what you will do is that after you do your imports, okay, so this installation has successfully finished, as you can see. You do your imports. You need to print your first of all, what I do is that I print the available models. This tells you what sort of models are available by default in MEGNet itself without you having to train models yourself. So if, for example, there's something called eForm MP 2019. This is basically the formation energy model that is trained on the 2019 version of the materials project. There's the 2018 one as well. That's basically when the paper was published, or rather when the models was first developed for the paper. So I would actually recommend that you use the 2019 models rather than the 2018 models. And you will see that there are also models for the band gaps, the log of the bulk modulus and log of the shear modulus as well. Okay, so the first thing that we wanted to do is to use our materials project API to basically grab our API keys. Okay, so one of the things that you need to do is to enter the API key yourself. Okay, so as I mentioned, your new API key is not going to work in Google Colab. So I'm going to enter my own API key, which is for the legacy system. So it doesn't matter because this API key is going to be deprecated very soon. I'm going to demonstrate the use of MEGNet on two different materials. One is BCC molybdenum. It has an MP ID of MP-129. Then I'm also going to demonstrate the application of MEGNet on Ly10G P2S12. Now, those of you who work on the battery materials know that this is a very, very famous solid electrolyte material. And this has this particular MPID over here. Okay, so and what you will do is that you can just run this code. This basically just says I'm going to use the MP raster to get the two materials, molybdenum and LGPS, by using their material IDs. Okay, and what you then do is that you basically get the structures themselves. So let me see. For me, it is not working. It says cannot find a version. Now, if you have this first line which says PyMegen equals to something, can you delete the equal? Yeah. Yes. Please. The first comment is correct. So please remove the PyMegen equals something. Everything after the equal sign, you should remove it, and you should be able to get it to work. Okay. Like I said, because the Google Colab actually runs on Python 3.7. The newer versions of PyMegen, like the newer versions of NumPy and everything, we no longer support Python 3.7. But the older version of PyMegen is fine. Okay. So so I'm going to paste my API key here in case to make it easier for you guys to run the code. Okay. So you just enter an API key here. In future, when you're running this on your own local computer, you can use your own your new materials project API key that you have. Now, here what I'm going to do is that I'm going to take all the available models and I'm going to use the model to do predictions on them, right? So so if you run this, okay, so it's not going to take too long. This is going to be a few seconds. Okay. So this basically loads the model. Each of the models, they basically then use the model to run a prediction. So for the log, bulk modulus and shear modulus, we just take 10 to the power of those numbers because what we want is actually the bulk modulus, not the log of the bulk modulus. For the rest, you just do the prediction. You just provide with the structures that you actually have, and you just directly predict the properties. And I'm just printing out the numbers over here. Okay. All right. Let's wait for this to finish. All right. So the prediction has completed. What do you mean by API? You have to run this thing first. So do not change any other things. Then use a double quote. It has to be in quotes, okay? And then it will work. Okay? So everything else, you just need to run the cells, right? So now I'm going to talk a little bit about the results, okay? So you see that the predicted formation energy for molybdenum is negative 0.003 eV per atom. So molybdenum is an elemental reference state, right? So for elemental reference states, usually we peg the formation energy of those elemental reference states as 0, and the model correctly predicts the formation energy of molybdenum to be close to 0, right? Now, I'm going to ignore, so LGPS has a negative formation energy, which means that you can, is exothermic when you try to synthesize it. The two properties that I want to show is here, right? So you see that the predicted bulk modulus for moly is 268 gigapascal, and the predicted bulk modulus for LGPS is 23 gigapascal, right? So for moly, we can actually look at the materials project data, right? So if let's say I go to materials project and I search the materials, and if you look at the materials project, they have all this information over here, but one of the things you have is the DFT calculated elastic constants. And what you see here is that the calculated bulk modulus for molybdenum, BCC molybdenum, using DFT calculations is 262 gigapascal. And what we have here is 268 gigapascal, right? So as you can see, the model is pretty accurate, right? And this is not surprising, okay? Because this data from the materials project was what we used to train the model in the first place. So this good performance on molybdenum is totally not surprising, but it is a good validation that the model is working as it should. Now, what is more interesting is the predicted bulk modulus for LGPS. This is a sulfide material, and we predict a bulk modulus of 23 gigapascal. And while this data is not in the materials project, my group actually has done elastic property calculations for alkali superionic conductors using DFT. It is in this paper over here. If you click on it, you will actually go to that paper. And our calculated bulk modulus for LGPS is about 27 gigapascal, right? And what you notice is that, again, this is very, very close to what the MEGNet models actually predict, okay? So, of course, we are not restricted to just things that we can find from the materials project. It is just the easiest way in which we can get crystal structures quickly and running predictions on them. So you can, by all means, you can do your modifications of this code, and then you can also use the models to basically run prediction on any of these properties on the materials that you're interested in, okay? Now, the other thing that I want to show you is that if you go to the GitHub page for MEGNet, you will see a lot of details about the implementation. Not only that, there are some usage. You can of course use the pre-built models. That was basically what the notebook has shown. Okay, so this is a much simpler example, but we just use it to predict a single material, which is again molybdenum. But you can also, there are also examples in which you can actually show you how you can actually build your own MEGNet model from your own data. Okay, so if let's say you are not satisfied with the materials project build models, or you have some very specific data set that you want to use the MEGNet architecture on, and you want to try to build your own model, hopefully with high accuracy, you can use this to basically train the models, and all these are all documented in this page. Okay, all right. Okay, so for the second half of my talk, I'm going to talk about overcoming data scarcity and quality issues with materials graph networks. Okay, so let me first outline the problem that we are interested in solving, right? And that problem is something that's very well known in material science, which is that high value data, so things that are the most accurate, or things like experimental data, tend to be very scarce, right? So one example that I have is basically the band gaps of materials, right? So you can always compute the band gap of your materials using many different DFT functionals, right? You can use the PBE functional. That's the cheapest. It is also the least accurate. but because it's so cheap, we actually have lots and lots of them, right? So you go to the materials project, you can easily get band gaps for 60,000 materials easily, right? Using the materials project API as I just showed you. There are more accurate functionals that people have developed that can predict the band gap to better accuracy. So things like the HSE band gaps or the scan functional, those tend to be a lot smaller in size, right? So for example, HSE band gaps, we can find a data set that has about 6,000 HSE band gaps, right? When we talk about things like the experimental data, which is usually what people are the most interested in, right? Because ultimately that is sort of like a ground truth, right? And for experimental band gaps, we only have about 2,700 band gaps, right? So this actually poses a problem. So this big data set is very useful for machine learning, but because it is the most inaccurate, we are going to basically make predictions of inaccurate data, right? Well, we have data sets that are much smaller but much more accurate, and when you try to build a machine learning model of them, your error actually increases, right? So the way that we decided to solve this problem is to use an approach that is very similar to how the way humans make decisions, right? So for example, when you try to make a decision yourself, you almost never just say, well, I'm going to use one data set, right? For example, when you think about a question like, well, should I buy stock in Tesla, right? You don't just listen to your Uncle Joe who will tell you his opinion about Teslas and the cars. You will actually start by doing some research. Maybe you listen to the podcast of Jim Cramer, and Cramer will tell you, well, bye, or no. You may listen to the sage of Omaha himself, Warren Buffett, and he may actually have an opinion about whether Tesla is a good buy or not a good buy. Ultimately, of course, the best thing that you should be doing is to really look at the finances of Tesla itself and come to your own assessment whether the stock of Tesla is overvalued or undervalued, right? Now, but basically, the key point here is that basically you actually incorporate multiple sources of information when you try to come to an informed decision, right? Now, so this is the way what we call multi-fidelity graph networks actually work, right? So remember, when I talk about the architecture of the materials graph network, we have something called the global state, right? And the global state applies to the entire graph network. And initially, we use this global state as a way of embedding properties that apply to the system as a whole, things like the temperature and the pressure. What we realize is that this global state can also be used to embed data fidelity, right? So for example, if we assign a fidelity level, let's say PBE is 0, HSE is 2, experimental is 3, and we embed that fidelity in this 16 length 16 vector, we can then, in essence, instead of building one machine learning model for our PBE data, one machine learning for our HSE data, and one machine learning model for our experimental data, we can now build a model that uses the entire data set of PBE, HSE, experimental, and GLB SC data. Okay? So, does this work? Okay, so let me first show you what happens when you try to build a MEGNet model with just a single set of data of the band gaps, right? So you notice that the mean absolute error of the PBE data is about close to 0.3 EV. Okay, so we can predict the band gap of PBE band gap to within 0.3 EV or so. However, the errors on our HSE and experimental band gaps, which are really what we really want, are much higher, right? Our HSE band gap error is greater than 0.5 EV. Our experimental band gap error is close to 0.5 EV, right? When we just build our MEGNet model using each of these data sets in turn. And the reason, as I mentioned, is because the HSE band gaps and the experimental band gap data sets are much smaller, right? And things like neural networks and especially graph neural networks are notoriously data hungry. You actually need a lot of data to train them very well. So what happens when we use our multi-fidelity graph network and we combine the largest data set, which is the PBE data, with at least one of the high fidelity data sets, or we combine all the fidelity data sets together, right? And this is basically what happens, right? The blue is basically the what we call the 2-5 model, 2 fidelity models, and the red is what is called the 4 fidelity models. And what you immediately notice is that we get a 40 to 50% improvement in our prediction of the HSE and experimental band gaps, right? So now actually our HSE and experimental band gap errors are almost in line with our PBE prediction error, right? Now, whenever I show this result, people are very skeptical, right? They think, wow, this is sorcery, right? Because you don't actually have more HSE data, you don't have more experimental data, but somehow the performance on your HSE and experimental data suddenly improved by 40 to 50%, right? You're getting something for nothing, right? And there's actually a good reason for this, right? So what we found was that when you plot the TS&E plot of the latent structural features with and without the PBE data, what you find is that with the large PBE data set, you actually have structural features that result in much more well-separated, that is much more well-separated with respect to things like the band gap, right? So here you can clearly see all the low band gap materials are in this side and all the high band gap materials are in this side. While without the PBE data, you actually get much worse resolution or much worse separation between the high and low band gap materials. And it is actually this improvement in the latent structural features that we believe is the reason behind the improvement in performance of the multi-fidelity MEGNet on things like the high value data like HSE and the experimental band gap predictions. Okay. Now, we actually even show that graph networks, unlike a lot of the machine learning models out there, can even be adapted to disordered crystals. So, for example, if you take the elemental embeddings and you treat a disordered crystal as though it is the disordered site as though it is a linear combination of the embedding vectors of the constituent elements, you can actually use the materials graph network directly and predict the band gaps of solid solution regimes in materials, and the accuracies are still reasonably good, right? And this is not something that you can do with a lot of the machine learning models out there. This natural interpolation of the embedding vector between for a disordered crystal. Okay. All right. Now, the second way in which you can handle the data scarcity issue is using what we call using the MEGNet model as an encoder, right? So this is actually not work from my group. This is actually a work that was done by the group of Anubhav Jain, where he basically benchmarked a lot of different machine learning models, including MEGNet, on various data set sizes that they have, right? So things like the yield strength, the exfoliation energies, they also have the band gap data, and as well as the formation energies, right? So what you will notice immediately from this plot is that when the data set sizes are very small, especially when it's below 10,000, so things like, for example, the yield strength or the exfoliation energies, the best models are never the MEGNet or the graph deep learning models, right? It is usually some random forest type model or or the AutoMap miner algorithm, which basically generates usually an ensemble learning model. Where the graph deep learning models, things like CGCNN and MEGNet actually really comes into play is when you actually have fairly large data sizes to train the model, and in that cases, those actually perform significantly better than your other machine learning models. Okay. Now, we decided that, well, I mean, it's well and good that you actually can use something like AutoMap Miner to try to predict properties at small data sets, but this is not ideal, right? As I mentioned, something like AutoMap Miner, they usually don't have structural features, and we really want to distinguish between polymorphs of materials. So we decided to come up with a way to actually solve this using graph deep learning, right? And what we did was to use MEGNet as an encoder. So instead of directly training a model, a MEGNet model on all the properties, what we did was basically we used our formation energy model, which we actually have a huge data set for. We extract out the latent compositional and structural features from the intermediate graph convolutional steps, and we use those as essentially descriptors for our crystal structures, and we use a standard feed-forward neural network to basically do property predictions, right? And when we train this model, this much simpler model, which just uses the formation energy MEGNet model as the encoder, we basically can show that we can achieve performance that is comparable to AutoMap Miner, even for the very, very small data set sizes, okay? So in other words, instead of trying to build a total graph network model as for every single property, if you just build the use the existing graph network model and for formation energies, which we know is reasonably accurate, then you build a simpler machine learning model on top of that encoding, you can actually get performances that are much better, and in fact comparable with all the other types of ensemble learning models that are out there. Okay. All right. Now, my final section of the talk is on overcoming the structural bottleneck, and this one of the ways in which you can do this is using what we call the M3GNet, which I'm going to talk about, right? All right. So hopefully from the all the previous 3 sections, I hope I have already convinced you on the value of machine learning for material science, right? So this is usually the way that in which you do a computational materials discovery process, right? What you have is some crystal structure that you come up with in your head, okay? Either you think about substitutions from existing crystal structures, or you do some some genetic algorithm generation, or some other means. You will then actually plug this into a DFT relaxation, and finally, if you need to, you use the DFT to do a property prediction model, like for example for bulk modulus or for some other properties, right? So what I have shown is that, well, you don't really need the last step, or rather you can at least replace the last step to a good degree of accuracy by using machine learning property models, right? So we have now, instead of using this small pipeline, this bottleneck of property prediction, we have significantly expanded our bottleneck for our machine learning property prediction, right? All the models that I've shown you so far, the prediction takes on the orders of a few seconds, right? So when I demonstrated the MEGNet prediction model, the entire notebook takes a few minutes to run, mainly because we have to load the models. But the property prediction itself takes a few seconds, right? And those of you who have done DFT property predictions knows that it takes much longer than that to predict the property of a material, right? The problem here is that all the models that I've shown so far are trained on DFT relaxed structures, and you need relaxed structures as an input to your model, right? And this means that you still need to do a DFT structural relaxation, right? And this is sort of not really gaining us a lot, because your DFT structural relaxation is typically a very expensive step in your materials discovery effort. So what we really need is to shortcut this process, and we need some way of doing machine learning based structural relaxation, right? So we want to expand this final bottleneck, and once we actually have this big bottleneck, we have a very big pipeline that we can use across from your candidate structure all the way to your property prediction. Now I'm going to show 2 approaches in which you can do this structural relaxation. One is to use existing energy models, and the other one is to build an interatomic potential, right? So the first way that we tried to do this was to use to apply the variational principle with MEGNet, right? So one of the key things about how DFT or all other quantum chemistry method works is the variational principle, which basically states that the lowest energy structure is your ground state, right? So it's very simple, right? So given that our MEGNet formation energy models can already predict the energy to a fairly good degree of accuracy, we can actually apply the variational principle to MEGNet as well. We basically just we just change our lattice parameters and atomic positions until we get a structure that has a lower energy, and we keep doing that until we get a converged low energy structure, right? And the way we do this is using what is called Bayesian optimization. And because we impose symmetry constraint, we call it the Bayesian optimization with symmetry relaxation, or what we call Bowser algorithm. So for those of you who don't know, Bowser is basically this final boss in Super Mario Bros. Okay, so that's where the inspiration for the name comes in, right? So the way that this works is basically you use a Bayesian optimization process to guess at a new data point. You then use your energy model to calculate the energy, and then you decide whether you want to generate a new guess for your data point, and you keep iterating until you basically get a relaxed crystal structure. Now, there's nothing special about using MEGNet. Okay, so here the energy model can be any energy model. In fact, you can do this with DFT as well. It will just be slow. But obviously, because we have a good formation energy model with MEGNet, this is what we did. And we basically apply this to basically take initial crystal structure. So for example, let's say you have cubic SRTIO3. There's only one independent parameter. If you assume symmetry, that's basically just the lattice parameter, and the Bowser algorithm will relax that to 3.975. If you have a triclinic, because you actually have much lower symmetry, you have 6 lattice parameters and all the atomic positions, and the Bowser algorithm will just relax everything, right? Okay. Now, what we showed was that basically by just such a simple concept, right, applying variational principle with our energy model, we can actually significantly improve the machine learning model predictions, right? So this is the predicted formation energy, bulk modulus, and shear modulus, log of the bulk modulus and log of the shear modulus for unrelaxed crystals, in which we just take the initial structures from experiments that is not relaxed. We use the Bowser relaxation, and we also did DFT relaxation on the crystal structures, right? And what we show is that when you actually have unrelaxed crystal structures, the predictions from your machine learning algorithm is disastrous, right? The errors are very, very large. In some cases, they are so large that they are useless for even stability predictions. Once you actually apply the Bowser algorithm, and you can actually get a much lower error. This is still not ideal, but it's definitely much better than 363 MeV per atom. And of course, DFT is expected to perform the best, right? So that's not surprising. Now, even with such a simple concept, we can actually already apply that to materials discovery. So I'm going to show you an example here, which is, I would say, one of the few examples where we apply machine learning to predict new materials, and we bring it all the way from prediction to actual synthesis to actually application, right? So the way that we did this was we chose ultra incompressible hard materials as our application field, and we started with about 5,000 ternary prototypes in the ICSD. We do combinatorial structure atomic substitutions on these 5,000 prototypes, and we generated unrelaxed candidates, about 400,000 unrelaxed candidates, right, of different crystal structures that can potentially be interesting. And what you will note, first of all, 400,000 is way too many structures for you to do DFT on. Okay, it will take you forever. And what we then did was to basically just use the Bowser algorithm to relax all the candidates, and we use machine learning models to predict things like the formation energy, bulk modulus and shear modulus, and then we screen all these materials using this criteria. So we want something like the EHAL has to be less than 100 MeV per atom for it to be stable. We predicted the bulk modulus. The bulk modulus has to be sufficiently large because we want hard materials, and the shear modulus also has to be sufficiently large, right? And after we just apply this simple screening criteria, we can, from all our 400,000 crystal structures, we can whittle it down to about 1,600, which is a good enough number for us to start to do DFT on. And then finally we do DFT relaxation. We then screen using a DFT EHAL, and we get about 143 candidates. And finally, my colleague at UCSD, Professor Jian Luo, then went ahead and tried to synthesize it. And he actually confirmed all 8 of those materials that he tried. But here are 2 examples of new materials that came out of the synthesis. This rhenium tungsten boride and this molybdenum tungsten carbide. And here is the comparison of the experimental XRD as well as the calculated XRDs. And you can see that they actually are in good agreement with each other. And Professor Luo's group also did pulse echo measurements of things like the bulk modulus and shear modulus as well as hardness. And again, what you see is that the machine learning model predictions as well as the DFT as well as the pulse echo measurements are in very, very good agreement with one another, right? So this just shows you the power when you actually start all the way from machine learning model. You now can play with a much bigger space of structures. Instead of doing most typical DFT screening works where you basically have maybe up to 1,000 materials or maybe a few thousand materials, you can actually start with 400,000 materials. You can even start with 1 million materials, and you can screen things very quickly to identify good potential candidates before you actually do your DFT calculations. Okay. All right. The second way in which you can alleviate the structural bottleneck is to build an interatomic potential, right? So an interatomic potential is basically something that parameterizes the energy and forces on the atoms as a function of the atomic positions. Okay, so in recent years, machine learning has become a very good technique to build an interatomic potential for any system, right? So the way that this works is basically you take the local environment around an atom, and you describe it using some local environment fingerprint. So that local environment fingerprint can be things like the distances and angles between the atoms or the neighbor density around the atom. And you generate a fingerprint, and you use machine learning model to map the local environment fingerprint to the potential energy surface, or rather the energies and forces on the atoms themselves. So this is actually now a very well established field, and there are many different flavors of machine learning interatomic potentials out there. So things like the neural network potential, the moment tensor potential, and so on and so forth. And they all perform very well, right? So this is not a major focus of my talk today. In fact, our group does a lot of research using machine learning interatomic potentials, but this is just an introduction to them, because we are going to do something similar but with graph neural networks. Okay, so all the machine learning interatomic potentials actually outperform traditional IAPs. Okay, so this is actually a plot of the energy and force errors. Left is energy and right is actually the force errors for all the different flavors of machine learning, all the variants of the machine learning interatomic potentials. And these are basically the same results for your traditional interatomic potentials. And what you see is that the errors from the machine learning interatomic potentials are much lower than what you get from your traditional potentials like EAM and MEM, right? Now, that's actually one of the main advantages of machine learning interatomic potentials, but it's actually not the key one, right? The key advantage of machine learning interatomic potentials is that they are highly automatable, right? This is actually a workflow that was developed in my group, where we basically did essentially a automatable recipe for generating an interatomic potential for any system. This was basically how we were able to generate so many potentials for so many different systems in a very short amount of time. The second advantage is that, of course, they are highly accurate, as this plot has shown, and they can handle reasonably complex chemistries, right? So, for example, we have built interatomic potentials, machine learning interatomic potentials for high entropy alloys and ceramics. These are very, very difficult, if in fact, whether it's even possible to get right with things like EAM and MIM, right? Now, the limitations, however, is that the complexity increases exponentially with the number of elements, right? So up to about 5 elements, 6 elements, we can still build interatomic potential, machine learning interatomic potential for them, and we can get reasonably high accuracy, right? Once you actually talk about, well, can we build a machine learning interatomic potential that can encompass the entire periodic table, right? What we call a universal potential. You can't really do that with any of these formalisms out there, right? Now, this is where we decided to think a bit outside the box, and we asked ourselves, well, we already have our MEGNet models. We know that it can perform very well for all our property predictions. We can predict things like formation energies. Why can't we actually build a potential using the materials graph network, right? And this is basically something that we recently developed, okay? What we call the M3GNet, okay? In case you're wondering why we call the M3GNet, it stands for materials graph with 3-body interactions. So the formalism can be any n-body interactions, but we stop at 3. It's also because 3, when you flip the 3, it looks like an E, so this is just update of the MEGNet model, right? And here we basically took inspiration from things like the Tursov interatomic potential. We incorporate many the 3-body interactions from as part of the bond features, and then other than that, everything else is basically similar to MEGNet in terms of the graph convolutional updates and everything, right? Now, why do we want to do interatomic potential using a graph framework? The reason is very simple. Because in a materials graph, every single element is just represented by an elemental embedding vector, right? There is no combinatorial explosion of the total number of features. We do not need to think about, well, are we interacting with lithium with sodium, or lithium with iron, or lithium with phosphorus, right? Basically, the graph-based representations takes care of all of that, right? And there's a very natural elemental representation for the chemical species of each element. So what this enables us to do is to be ambitious, right? We decided to build an interatomic potential for the entire periodic table using a graph deep learning based approach. Now, the first thing we did was to basically just test out the architecture itself. We use the same elemental training data as we did for our benchmark of the machine learning interatomic potentials, things like FCC, nickel and copper, lithium and moly, silicon and germanium. And essentially we show that what this plot basically shows is that if given the same training data, our M3GNet architecture actually performs very comparably to the machine learning interatomic potentials that are already out there, and much better than your EM and MIM potentials, okay? So in other words, the architecture itself is not going to be a limitation in terms of developing an interatomic potential, right? Now, if we are just using this to build an interatomic potential for just a few elements or just a simple 3-elemental system, that's not going to be very exciting, right? I mean, we can do that with machine learning interatomic potentials today. So what we realized was that there's actually a lot of underutilized data in the materials project. So since 2012, when materials project first started, there's about 100,000 DFT structural relaxations. So we actually have on the order of 100K energies, 10 million forces, and 1 million stresses for all the different crystal structures out there. And this entire data set actually covers 89 elements of the periodic table, right? And what we can do now is that instead of building a potential for some limited chemistry, we can just take this very, very big data set and we can just throw it into the M3GNet architecture and build what we call a universal interatomic potential for the entire periodic table. Okay, so that's basically what we did, and we can show that we can build an interatomic potential that can predict the energies to within about 33 MeV per atom. Very not as low as if we just build it on one element, but remember this is for 89 elements of the periodic table, so this is actually very good for that purpose. We can predict forces to within 0.07 eV per angstrom. Again, very good, right? This is good enough for us to do structural relaxations with it, and stresses are a bit more mixed, but again we can get the forces to within about 0.419 GPa, right? Now what this enables us to do now is that we are now able to do DFT-free structural relaxations using M3GNet interatomic potential, and we can, after we relax the crystal structure, we can actually predict the stability of materials using M3GNet as well. So this is basically just a sample of 3,000 structures in the test data set. We show that basically the energy of the ground state that we get from M3GNet relaxations is in fact very close to what we get from our DFT calculations, and the volumes that we get from our M3GNet relaxations is again very close to the DFT relaxed crystal structure volumes. So here on the right we show the stability prediction, where we actually calculated the E above Hall for the systems based on M3GNet as well as DFT, and you will see that the distributions of the E above Hall are very much similar regardless of whether we are talking about all chemistries or just oxides in general. Okay, so this has led us to start a new initiative, what we call Matterverse.ai. So we see this as essentially a complementary website to the materials project. Okay, it's a complementary initiative. So the materials project is basically just DFT calculations and DFT predicted properties and structures. As you can see, today the materials project has about 144,000 materials. That has not changed for a long time, and the main reason for that is because there's a limitation in the number of structures that are being generated that the materials project can calculate, right? What we aim to do is to really change that, right? Rather than just rely on DFT, using M3GNet, we are going to target huge database, more than 1 billion structures, and we are going to do machine learned property predictions. So things like the structures, the band gap, the energies, the stability, the phonon dot center, and so on and so forth. Okay, and we are going to build this active learning loop with the materials project. We are going to prioritize some of the structures and pass them on to the materials project for calculations and screening, and we are going to use take some of the new relaxations and training data and use it to further improve our M3GNet potential. Okay, so so this is the current progress. Okay, so we have today have about 30. We already have done about 31 million structures. Okay, this is generated from 5,000 structural prototypes, and we have with 80 elements, and that out of these 31 million structural prototypes, we actually get about 1.8 million with MEGNet predicted EHAL of less than 0, and we actually took about 2,000 of them to confirm with DFT calculations, and we show that actually the agreement is pretty good. In fact, the hit rate is very good. We can get about 80 to 90% hit rate if we choose a cutoff of about 50 MeV per atom as a stability cutoff. Okay, we have also used this data to conduct what we call a massive scale for search for new lithium superion conductors. So because we have a universal potential, we don't need to just do relaxations, right? We can do MD simulations as well. We can do this MD simulations for a large number of different chemistries. These are all lithium containing materials, and what we can show is that basically doing this, we can actually identify good lithium superion conductors, and the existing ones, they all actually fall within this regime in the of this plot, and there are actually a lot more data points out here that we are now exploring. Okay, All right. With that, I want to do a demo. So you can actually go to Matterverse.ai today. Okay. And let me stop my share. And this is basically the Matterverse.ai website. Okay. And today, let's say you are interested in LIYCL, you can actually, this is basically, you can search for lithium yttrium chloride type materials. This is all ranked by the predicted E above Hall. And if you click on this, you can see the crystal structures as well as things like the predicted properties such as the formation energy, the band gaps, the bulk modulus, shear modulus, and so on and so forth. Okay, so this has this greatly expands the number of materials that we can potentially explore and work with. Okay. All right. Now, before I end the talk, I want to do a second hands-on demonstration of how you can do crystal structure relaxations with the M3GNet universal interatomic potential. Okay, so again, you can go to colab.research.google.com. You open a new notebook. You go to GitHub. Is again Materials Virtual Lab. Instead of MEGNet, now you go to the M3GNet repository. There are 2 example notebooks over here. Okay, so let me switch to Google Colab so that we can look at that. Okay, so let me open the next one. So I'm going to skip the cubic crystal structure test first because that takes a fair bit amount of time to run. I'm going to show you an example of a relaxation, right? All right. So this notebook shows you basically how you can do a crystal structure relaxation for any arbitrary crystal structure using the M3GNet universal potential. Okay, again, you need to install these 3 things. So we will let it run. Okay, so again, we are going to use MP raster to basically obtain our an initial structure for lithium iron phosphate, which is a very well-known cathode material. And in the M3GNet repository and package, we have already pre-built our potential, the universal potential, and that universal potential is actually, you can use it out of the box without any further training. Okay, so the one that we need to import is basically from m3gnet.models. You need the relaxer, which basically does crystal structure relaxations. So what that does is that it basically uses the M3GNet potential together with ASE, which is the Atomic Simulation Environment package, to basically perform crystal structure relaxations. Okay, so I think that install is almost going to be done. Okay, that install is done. So now we can do these imports. And again, for Mster, you actually need your API key. You can use the one that I gave earlier. If you go to the materials project, you search for lithium iron phosphate. The materials project ID is actually MP-19017. So we are going to get the LFP structure from there. And what I show here is basically, I'm going to artificially strain the LFP structure, okay, by some arbitrary strain of up to 5%. And I'm going to apply the strain to the structure, and I'm going to perturb the atomic positions as well. This is just to generate some perturbed structure that we are going to do structural relaxations on. So if you do this, it actually is very fast. You should get it within a few seconds. And then I'm going to ask the relaxer to basically relax the crystal structure, okay? And this is not going to take too long. So this is just a Jupyter command to basically time this particular step. I just want to show you how quickly that relaxation actually takes. Most of this step is actually involved in downloading the potential and initializing. So if you are using this for a lot, much bigger crystal structures, a lot of crystal structure all at once, it's not going to take this long. Now, so here it says that the wall time is 36 seconds. So it does take a bit longer than if you're running on a local machine. So if you run on a local machine, you should be able to get it within less than 20 seconds. Okay, so definitely much quicker than your standard DFT calculations. Now, so this is basically just showing you what are the results. So the original lattice parameters are this, and this is basically the strain lattice parameters. And what you will see is that the relaxation actually brings the lattice parameter much closer to what the strain lattice parameters are supposed to be. And you should also be able to check the differences in fractional coordinates, and the fractional coordinates are definitely much closer, okay, within 0.10 to the power minus 3 of the original crystal structure, the original lattice parameters of fractional coordinates of LFP, okay? All right, I'm not going to show the cubic example, but rather I want to show the results of that relaxation, because so one of the things that people are skeptical about is, well, if you have a potential for the entire periodic table, really how well can it work, right? So to actually prove to you that, prove to everyone that it will work, we actually took a set of about 90 cubic crystal structures. Okay, so all these are cubic crystals. Okay, and they actually have DFT, relaxed crystal lattice parameters, as well as experimental lattice parameters. And we actually use M3GNet to relax all these crystal structures, right? And you can look at the percentage error with respect to the DFT lattice parameters over here. And what you will see is that for most of them, the errors are less than 1%, right? So in other words, we can get very, very accurate lattice parameters using this M3GNet potentials. There are a few errors that are slightly higher, like for example for BCC cesium or cesium iodide, the errors are somewhat bigger, and the reason is mainly because there's a lack of training data in things like the cesium system and the iodide systems, and that's probably the reason for these errors. Okay, but otherwise this is a proof of concept, right, that the universal potential that we have developed really actually works quite well. Okay, so just to conclude from this seminar, that the metaverse is actually a very complex thing, right? When we think about the metaverse in terms of things like chemical complexity and structural complexity, you have anywhere from something very simple like a BCC metal or FCC metal to something simple crystal structure like strontium titanate with more chemical complexity, not too much structural complexity, to something like a polymer with less chemical complexity but a lot of structural complexity, all the way to the structures that I show you in the initial stages, which is polycrystalline material with grain boundaries, and this is a high entropy alloy, so there are multiple different elements in there. So there's a lot of chemical and structural complexity. So hopefully from the talk today, I hope that you are convinced that machine learning actually can help greatly expand the way in which we can explore this metaverse, right? We are using graph representations for materials. We can do accurate and fast property predictions. Okay, we can build universal interatomic potentials, not just interatomic potentials that are just constrained to one chemical system, for the entire periodic table, right? And this really has enabled what I call massive scale material science, right? Things which we can do at a scale that was not possible with just DFT calculations. Okay. With that, I thank you, and I just want to acknowledge my group. Okay, so this is a group photo that was taken pre-COVID during one of the PhD um, graduations, and most of the work that was done on the graph neural networks was done by Dr. Chi Chen. He is now actually a researcher at Microsoft Research. The interatomic potential work was done by Yunxing Zuo and Ji Qi, who is now actually an intern at our Lawrence Livermore, is actually the one who is working on the metaverse and the search for lithium superconductors conductors. Okay, and with that, I thank you, and I'm happy to take questions.